Alright, so basically at some point I need to explain like some concepts which I guess are mostly to do with particle kinetics rather than kinematics, but yeah, sometimes and even like in your first year physics course, you've seen pulleys and you've seen springs, right? But I'm going to try to break them down because there's a little bit of intricacy in terms of how they work. So we'll start with that. Oh, actually, sorry. I'm a bit all over the place. Let's start with where we're at, right? Structure. So I like to start broad. So we're in dynamics. We're still doing particles, right? So everything in terms of your midterm should stay within this deceptively simple tree diagram. But yeah, we're tackling the kinetics part rather than the kinematics part now. So just a quick recap. Kinematics is to do with the motion of objects, right? Without so much consideration on the forces which cause them. But kinetics is all about Newton's second law, right? It's all about that force equilibrium. Yeah. Oh, sorry, not equilibrium. Force equilibrium is a statics concept, but it's all to do with Newton's second law and then taking the sum of the forces and stuff like that. Okay, so again, let's reframe this. So here's a different tree. We're talking about this section today. It's the particle kinetics, right? Newton's second law, your work energy methods, and impulse-momentum methods, right? Which the derivations come from Newton's second law. So let's just explain the work energy methods quickly. There's something I like to call the Holy Grail formula. It stems from what the mech school calls it. Looks like this. We'll cover it in more detail as we go. You might have seen different notation for this in the civil school. To be honest, I don't actually know what they call these constants in the civil school, but this is what I've labeled it as. Let me zoom in for you. It's saying that the work done from state 1 to 2, right, is equal to the change in your kinetic energy, right? So that's kinetic energy. Plus the change due to your gravitational potential, grav potential energy, and plus your change in spring energy, spring potential energy, I should say. Right? Some systems don't have springs, so in that case, you can ignore that change in spring energy. So the impulse-momentum method, I might move that out of the way so I have a bit more space here. The impulse-momentum method is the impulse from state 1 to 2 is equal to the integral of the sum of the forces with respect to time from time 1 to time 2. If you want to think of it linearly, which sometimes you can, it's just saying maybe the net force multiplied by change in time, right? Okay. Does anyone have any questions? These will be the things we cover today. So again, Newton's second law, which I'll write it down as well. Newton's second law is this one. Newton's second law, work energy methods, and impulse and momentum. So we'll try to do Newton's second law and work energy methods in the first half, and then impulse momentum methods in the second half. Okay. Oh, sorry. Is anyone still copying that? I'll zoom in. Yeah. Sorry. As I was saying about pulleys, right? I'll explain pulleys and strings and springs a little bit more, because these are kind of concepts which are always in the background for Newton's second law, but I'm not sure if they're like explicitly talked about in the lectures, stuff like that. So pulleys, right? They look like this, or like this. There's essentially two types. We have our fixed pulleys and our movable pulleys, right? So I'm just gonna concentrate on this, right? So if we use Newton's third law, which is to do with kind of our free body diagrams, the fact that we can analyze the forces when we cut certain sections like this. How does this force equilibrium work? Do you know what I mean? So this should be sum of the forces in y is equal to 0, sum of the forces in x is equal to 0. How does this work if we have tensile forces due to that same rope but pulling in different directions? So want to have a crack at this? This is balanced out by reaction forces. So if you have a fixed pulley, it's basically attached to a pin support. You can think of it like that. However, why we don't focus on that pin support is because we don't care about the reaction that is happening at that pin support in the dynamics portion of this course. We do care about it for rigid body kinetics, but I'm 99% sure they don't have that in the civil version of this course. Yeah. So for movable pulleys, right? Even though these are moving, in this particular case, we don't have any horizontal forces. Even though this is moving, we're actually still considering it as a static equilibrium, and that's because that movement will not have a velocity. Not have an acceleration, right? It will probably have a fixed velocity, right? So basically, in this particular pulley system that I've drawn for that movable pulley, we have two ropes. Let me zoom in. We have this rope, and then we have this rope. So when you have two different ropes, you can actually have two magnitudes of forces, like two different magnitudes of forces, right? And then they have to balance each other out. So because these are two different ropes, this rope can have twice as much force on it as the other rope. But the amount of tension in one rope has to stay consistent for the entire rope. So this rope, both those T's have to be equal. Does that make sense? Okay. That's that rule that I wrote here. Tension is consistent throughout each rope. The other thing we assume, this is just kind of a random assumption as well, these pulleys are massless and frictionless, so we don't consider the effects of friction pulling on that rope, like sliding here, and we don't consider the weight of it, essentially, right? Okay, so now we have to talk about something called mechanical advantage. Oh, actually, let me just quickly comment on this. In the mech school, they talk about motorized pulleys. We won't, so yep, disregard the motorized pulleys. But mechanical advantage, this will come up a little bit in the course, and yeah, let me just show you the examples I've got here. So let's take this first example, right? So firstly, what type of pulley is this?
Fixed pulley.
Fixed pulley, very good. So it's not going to move, essentially, right? The force in this rope we can actually calculate, right? So, if we just analyze that section, it's essentially saying that the tension in this rope is going to stay consistent, right? So that force is going to be the force of that box, right? Even though it's coming at a different angle, right? It's balanced out by the reaction forces in that pin support or whatever. But the idea is that we can calculate it for the tension in that rope, here to here, here to here, and then it stays consistent throughout that rope, right? Okay. So, wait, it's alright. Did I do something wrong here? No, that's right. Okay, good. So the idea is this has a mechanical advantage of 1, right? But sometimes we can have an increased mechanical advantage or a decreased mechanical advantage. So let's look at this, for example, right? This system has two pulleys. One of them is fixed and one of them is moving, right? And mechanical advantages can only really happen when you have a movable pulley and you have two different ropes. Does that make sense? Do you see how I've drawn the ropes with different colors here? Right? So basically the tension in this rope is equal to the weight of the box. Agree? But how do I say this? we have a mechanical advantage of 2 because when we analyze this section, let me draw it out. Let's call that T, right? This red rope is actually only taking half the amount of tension each. Does that make sense? It's the same thing as I drew before, this one, but instead of calling it 2T, I've called it T, because if we look at this section, we've called that T, essentially. T is equal to mg, right? And so that force that's required to pull it is equal to T on 2, which is equal to that divided by 2. So you're going to need less force to pull this box up because we have this moving pulley involved, and it gives it a mechanical advantage of 2. Does that make sense? So sometimes you'll see questions which have pulleys in it, and you might not understand fundamentally that concept of mechanical advantage, but you want to think about this. And sometimes we can have mechanical advantages of 4 if you have multiple moving pulleys. You can Google up examples. I don't think I've included one in my notes here. But yeah, you can have like very high mechanical advantage multipliers, and then it saves that effort. Effort, is that the right word? I don't think that's the right word in terms of mechanical engineering, but yeah, you know what I mean. It saves the human some effort, you know what I mean, in pulling it. So this might seem like you're just spawning force out of nowhere, but it's conserved because it's balanced out by the displacement, right? So you have to pull twice the distance at half the force for this particular case. Yep.
What is mechanical advantage?
Let me think about that. So if you have okay, let me start from the example here. So we have a mechanical advantage of 2, and it means I have to put in half the amount of force to pull the rope.
Oh, is it like the ratio of actual force versus
Yes. So I guess you can call this your load. So it's a ratio of that load to how much force you actually need to pull, I guess. Yeah. I don't know the mechanical engineering terms. I'm sure there's somewhere.
Like the force that you're pulling at the end. It's like like a lever or something like that.
Yeah, I know the word effort is involved, but I think that's only for that whole like lever system. I'm not sure if that effort word is correct when we're talking about pulleys. But there are multiple types of mechanical advantage systems. In mechanical engineering, you deal with the lever system, and you deal with cogs, or whatever it's called. Yeah, these ones, the ones that spin. Yeah. That's a mechanical advantage system as well. Yeah.
Well, that's just a lever.
I mean these cogs here, you know. These
Yeah.
ones. Yeah.
They're actually just like.
Oh, are they?
Yeah.
Damn. Okay. Well.
Think about it.
Yeah, I'm learning from the dynamics portion of this course as well, just as much as you guys are. All right, so hopefully that doesn't. Hopefully you still have some confidence in me. But yeah, that's just a nice way of saying I don't know what I'm talking about. Wait, actually, I'm gonna.
What's in those cogs? Is it a bigger one? Imagine it's like just a whole stack of these like levers.
Anyone gets cold, let me know.
Yeah, okay.
I'm boiling a lot
But
here.
is it bigger the cog is larger than mechanical advantage?
The longer it takes to spin around,
Yeah.
the less effort it takes to do it.
Yeah.
Okay,
Higher.
so this is a Newton's second law question, right? It has a couple of other elements in it. Firstly, it has mechanical advantage, and like our pulley thing that I've been talking about, and it has friction involved, right? So this will be a type of question which could test your understanding in multiple areas, right? So in Newton's second law questions, you should generally draw out the free body diagram, right? But let's think about what we just said. So this is a fixed pulley, right? This is a moving pulley, right? And we've created this system which has a mechanical advantage now, right? So, wait, does it? Yes. So basically, the tension in this rope is 100 and has to stay consistent for that rope. But there's 2 bits of rope which are pulling on this box, correct? So we have 100 newtons of force on both these parts of the rope, right? Does that make sense? Yeah. Okay, next we can calculate the weight of the box because we're given its mass, right? So 40 times 9.81, like that, right? Okay. Generally, how we solve these Newton's second law questions, which look like this, is you start with the weight, because usually you're given the mass, and then you do the normal force, and then you do the friction, right? That's the order. Okay, so to calculate the normal force, right, firstly, just focusing in the y direction, are we in static equilibrium? Yes, we are.
Yeah, sure.
Because we wouldn't be in static equilibrium if the box was being yanked off the ground. But since the box isn't moving up and down, right? Well, like that's a pretty safe assumption, right? We're in static equilibrium in the y direction, right? Okay, so that means that we can look at the vertical forces, N, and then we can add on 2 lots of our 100 that's at an angle of 30 degrees. So we take that vertical component, sine 30, right? And we should also subtract its weight, right? All makes sense? So this gives us the normal force is equal to 292.4 newtons. So, sorry, my notation's a bit weird. This one is to do with its units. This one is to do with the force that we call normal force, right? So it's not, there's not an n variable on both sides. That's what I'm trying to say. Okay. Next, are we in static equilibrium in the x direction? Yes? No?
Yes.
We have, for these questions which involve friction, start by assuming we are in static equilibrium and solve for that. And then, basically, if our friction value has exceeded the static equilibrium threshold, then we're actually in dynamic, like where we're moving, basically, right? So start with the assumption we're in static equilibrium first. Okay, so that's what I've done here. Sum of the force in the x direction is equal to 0. So, x direction we have 2 lots of 100 cosine 30 degrees. And then we have to subtract this unknown friction force, right? Which we solve for. This friction force is 173.2 newtons, right? Okay, so, we want to calculate something we call the static threshold. I'm going to explain this through an analogy. Okay, so your static threshold is like a bucket of water. Okay, so your static threshold is how much water your bucket can hold, like the volume. Let's say it can hold like 5 liters of water or something, right? Your FF, your friction force, in terms of what we've calculated as if it's in static equilibrium, is how much water you're going to pour in your bucket. So if we go over, if we overflow the bucket, we're actually moving now, right? If we underfill the bucket, we're in static equilibrium and the box is not moving. Does that make sense? And that the analogy, okay, I'm going to continue the analogy. I'm going to double down on the analogy, right? So how full this bucket is determining essentially, actually, yeah, okay, well, let's continue and I'll go back to the bucket, right? Okay, so we'll calculate this. We are given the constant. We are given the constants, the static friction constant and the kinetic friction constant. So when we're calculating static threshold, always use the static friction constant, right? Which is 0.5 in this case. And that N is the normal force, right? Just like that. Okay, so right off, based on these numbers, right? Oops, let's pretend you didn't see that. So this is how much water we're going to pour in the bucket. This is the size of the bucket. Is the bucket going to overflow?
Yeah.
Yes, which means our box is moving, right? We've overcome the static friction threshold, right? So since this is greater than this, we're dealing with kinetic motion or whatever. And then we're going to use a new constant that we're going to calculate now called the kinetic friction constant. So this kinetic friction constant is basically saying that while this box moves, no matter how fast it's moving, we're going to subtract that driving force, whatever's causing it to move, by a set amount, Fk, right? So regardless if we're not yanking the box, we're pulling the box really, really hard or just hard enough for it to overcome static friction, we're going to subtract off this kinetic friction constant. Oh, okay, I've done it one step here. Okay, so because we're moving, we have to use our new Newton's second law, right? Sum of the forces is equal to ma, right? So basically, this is kind of like a net force that, that the rest of the forces is equal to. So all the forces acting to the right are these ones. Just went out that one. But instead of FF, we're gonna call it FK now, right? And then that FK is equal to that kinetic friction constant multiplied by the normal force. And our kinetic friction constant is usually going to be less than our static one, but it has to be at least equal to it, if that makes sense. Right, so if this one's 0.5, this one can be 0.4, but the max number you're going to find is 0.5. Okay, so that whole thing is equal to 116.96, right? And we know the mass of the box is 40, right? So we can just divide the right-hand side by 40, and then our acceleration of the box is 1.406 meters per second squared. So just intuitively, which way is the box moving? Very good. So that acceleration is going to the right. Okay, cool. So if you want to think of this graph that I drew, I think in the very first lesson, a box is moving to overcome that static threshold, and then it's always going to subtract off this constant. Right. Any questions? Okay. So next, oh sorry, I'll leave that there in case anyone's copying that down. But springs, right? So springs have an equilibrium, right? So every spring will want to return to a stable state, right? It's called its unstretched state. But if you pull the string in the axial direction, it acts like a rope, right? So it's gonna take on tension, and it's gonna extend, right? So unlike a rope, which might extend a negligible amount, a spring will physically extend its length, right? But a spring will also do a similar effect in compression, right? Where if you push it together, it's going to want to return to its equilibrium and push back out, right? Okay. So there's some properties to do with springs. So firstly, it's stiffness, right? So for those of you who've done engineering studies, you might have heard of like elastic modulus. Elastic modulus is in it's like a force over area. So this is like some material property divided by a cross-sectional area, right? So it's like in 2 dimensions, I guess. But this one, the spring constant, is over 1 dimension. So it's how much force will cause it to move a meter, essentially, right? For this spring. Wait, no, it's alright. Anyway, so it's like a 1-dimensional version of elastic modulus, right? Its unstretched length we can call LO. I might have called it XO in some notations for some of the questions. But yeah, Hooke's law is that the force of the spring is equal to that stiffness multiplied by how much you're gonna stretch the spring out. So that delta L is the difference between its original length. So if this is its original length, right, and we pull it and it wants to stretch out even more like that, that is delta L. That is the amount it's changed, the length that is changed from its original position, right? Spring energy. This is a part of our kinetic, what's it called? Part of our big work energy formula, which you'll see down below a little bit more. I'll explain that once we get to it below. But yeah, so the deformation of the spring, just drawing on this diagram again, this is L final, I guess you can call it. I didn't call it. Yeah, okay. But basically with these kind of questions, we're going to analyze different states in time, right? So that's where these subscripts come from, A and B. So it's like at the final position of A or at the final position of B, you know, that change is just going to be whatever that is extended to. So say this is time A at state A, let's call it. Looks like that. You know, it's gonna be like this then, right? But at state B, let's say that the spring's actually compressed, right? Then this is going to be LB, and this is going to be change in LB, right? So how much it's moved from that original position. In this case, it's compressed, right? So that's going to be change in LB. That's going to be LB. And then if it's if it's actually compressed, then our length is going to be a negative number, right? But if it's stretched, then that change in length is going to be a positive number, right? Makes sense. So this, even though it's a length, the change in length can be a negative value, right? Okay. Here I've included some like other types of notation which you might see as well. Wait, sorry, I kind of misled you. I don't think I've ever called it XO. I think I've always called the unstretched length LO. So sorry about that. Probably don't include that in your notes. Yeah, but yeah, this is really confusing. So like the notation, yeah, for this section is probably, it might throw you off like in your calcs. So just make sure you have this page ready when you're doing the questions. Okay. So now we're up to work energy. So here I've called the states A and B, but I think for momentum I might have called the states 1 and 2. So yeah, so basically your states can be like, in this case I've called it, you know, states A, B, so states in time. And then the objects, I think I might have called them object 1, 2, you know, whatever. But I might have flipped it the other way around in the momentum one. But as long as it's clear what we're talking about. In this case, we're talking about states, right? Yeah. So the change in work, the work done from A to B is denoted like this. And yeah, it's equal to kinetic energy, as we've said. Kinetic energy, gravitational potential energy, and spring potential energy, right? which was that formula I showed above, right? Oh, hey.
Double check the IT, the system crashed.
Oh,
All
really?
the SOE computers crashed. So what are the laptop, desktop in one?
Yeah.
So everything crashed. And so we need to wait for the further instruction from Microsoft. So it's not from here, also the USA. So everything crashed.
Okay.
So if your computer is non-SOE, SOE means not belong to the university, centralized. And then everything crashed.
Okay.
Yeah. And so you guys okay? For the coming quiz, the marks for the lab assignment already, right?
Yes.
Okay. Thank you.
Yeah, no worries, thank you. Alright, so let's look at the formulas. So basically, okay, for what it's worth, this is my favorite topic in dynamics, just because, okay, well, personally for me, it's just because I can do the questions like consistently and get it right, but it's also because I feel like everything just falls under this big umbrella equation, and it turns out to be really nice when you plug everything in correctly. So let's break down this formula a little bit more. So in blue there, on the left hand side, this is the work. So the work is basically the force, the external force, right, multiplied by the displacement, the change in displacement from A to B, right? So again, A and B are referring to states in time, right? Here's the integral version if you want. But yeah, so that's displacement, right? When I'm talking about external force, there's basically only two cases you're going to see for external forces. One is someone pulling on a rope. So this is like, I guess, the external, sorry. This is like a mechanical kind of work that they've done to like pull on a rope or something. Do you reckon this adds or subtracts work from a system?
Adds.
Very good. So this adds energy, right, essentially to a system. What about friction? So friction, we know, opposes the direction of motion. Opposes the direction of motion and the forces which go in that direction, right? So do you reckon that friction adds or removes energy from a system? Very good. So that's literally like as complicated as it gets, right? But you can just see it put into practice. These are literally the two types of work that I've seen in these questions before. And yeah, how they're presented generally in terms of S is, for the case of someone pulling on a rope, how much work they've put in is, a function of that force as well as that displacement, right? And then that displacement, you can track it by how much the rope has moved, right, from its original position. And then I guess you can think of it like how much the rope is slided, right? Yeah. And then for the case of friction, right, that's just, that one, it won't be as hard to spot, but it's just the displacement of whatever object causes friction. Yeah. Okay. Next we have the kinetic energy, right? So this one should look fairly familiar. I know, like, when I did physics in high school, I called this kinetic energy like KE, but I would say this notation is just a little bit nicer. It's talking about the change of kinetic energy, and then you're using one letter to represent it instead of two, and then it's talking about which state it's going between, so A and B. So I think it's a little bit cleaner. This one in high school we called it gravitational potential energy, right? But yeah, again, I would recommend that you stick with this notation, and this one's your spring potential energy, right? Yeah. So let's look in particular for gravitational potential energy, right? So, I mean, this is to do with velocity. I'm not sure if you guys have seen. Surely you've seen this before. I think you might have seen it in first year physics for kinetic energy. But for gravitational potential energy, it's to do with the height above some datum, right? So height So a datum is like a reference point, right? So actually this formula is kind of like it's kind of idiot proof, right? So regardless of where you put your datum, the formula will still work essentially. So if I set the datum as the floor, right, it means this is the reference point, right? And let's just say like the height of this desk is like HA or whatever, and then HB is like height of my head or whatever. Then it will work. But if you set the datum as like, I don't know, the roof, right? And then we do the same thing, you're gonna get the same numbers, right? All that matters is the change in height between that point. So like this to the top of my head, as long as those numbers all work out, it's fine. And these numbers for the HA and HB can be negative. So if you imagine, if I set the datum as the roof, right, these will be negative numbers because the height will be going downwards, right? Yeah. And just gravitational potential energy, you've probably learned in physics or whatever that if you have an object that's higher, it has a higher gravitational potential energy. You have an object that's lower, it'll have a lower potential energy, right? Yeah. Oh, so like, but what matters is that change in height. Sorry. So if something goes down, right? So say we have like, yes. So let's do that again. So say there's a ball, and for some reason it bounces on this table, and that's state 1 or state A, and then it bounces onto my head, that's state B, right? Has it increased or decreased in gravitational potential energy?
Increases.
Very good. But if it rolled off my head and dropped on the table, it would decrease, right? Yeah. Okay, next is spring potential energy, right? So again, these formulas can be broken down further. Let me just. So I always get it the other way around, so I'm making sure that I didn't screw it up. This one is LB minus LO, and then that's squared, and then this one is LA minus LO. Right. So basically, you can imagine like if I pull a spring, right, and then I keep pulling it, it's gonna require more and more force for me to pull that spring out because it wants more and more to return to that equilibrium length, right? So that's what this accounts for. So that squared portion, it's kind of accounting for that. The fact that yeah, as you get further and further away, it's going to require like a quadratic amount of energy, right? Okay, any questions so far? Okay, let's do another question. I'm running a little bit behind schedule. Okay, so here's our problem. So we have a 7 kilogram collar. A collar is like this kind of sliding object that stays on this trajectory, right? It's like a cylinder shape. Yeah, and it has to stay on this path. That's also kind of like a cylindrical rod, right? And then it slides with negligible friction, so we don't have to worry about like the effects of friction, like subtracting, like removing energy from the system, stuff like that. Yeah. Okay, so state 1, the collar is released from rest at the bottom, and it moves up the shaft under a constant force, pulling force, right, of 200 newtons. Calculate the stiffness of the spring it must have if the maximum compression is to be limited to 75 mil, and this is actually a fixed pulley, right? Wait 1 second. Okay, basically that maximum compression of 75, right, for this spring, it just happens to be that from where this is attached to the top of the spring is 75 mil, right? So our second state is just going to look like that, where the spring is compressed and this rope lines up perfectly like that, right? So for this particular question, we're going to call the states 1 and 2. So states in time, they're going to be denoted by 1 and 2. And we're going to be calling the objects A and B, right? Because A is our slider and then B is that fixed pulley, right? Okay, so the first thing we should do for questions which involve a rope and a change in the length of the rope is we should draw these kind of like triangles, right? Because it can be simplified using Pythagoras essentially, right? Because we don't know how long the rope is, right? The rope could extend infinitely, right? But what we do know is the rope which is in between that pulley and the collar. So that will change, right? So just intuitively, right? Is the rope going to get shorter or longer in between that section? Very good. So when it gets pulled, it's going to be shortened until this length, right? So this is to do with work, and this is to do with that displacement part of work. That's what we're calculating right now. So we're analyzing that geometry. So we're going to call that that diagonal length of the rope R. Okay. So we're doing it in meters. So we just use Pythagoras, as you can imagine. Like that, right? Okay. You know what else we should do? We should measure. Okay, we should measure the amount the spring will be displaced as well in the state 2, right? So what I mean is, so the spring starts out like this, right? And then we can measure how we can measure that change essentially using geometry as well. So we're going to call that x2, which is the change state 2 of the rope, right? So that's going to be like that essentially, right? So L2 is equal to the original, it's going to be equal to whatever original length of that spring subtracted by, we know it was 75 mil, right? Which is that in meters. Okay, so we actually don't care about what the original length of the spring is, because using this formula, these LOs cancel out, right? So x2 is simply going to be negative 0.75 meters, okay? So now we've sorted that for the spring part, and we've sorted one part of our displacement component for the work part, right? Okay, so the change in rope length between slider A and the pulley B, right? So this will be the final state, right? Where we've pulled the rope the whole way, and then our slider's gone to the top, and then we have that rope up, right? So that's what geometry 2 that represents. So that's equal to 0.225. Sorry. So that's what the rope length will be between the pulley and the slider in state 2, and then that's what the rope length was originally, and then obviously a change is the final one subtracted by the initial one, right? And so the change is going to be that, right, in terms of that distance here. But what we actually care about is how much the rope is pulled, right? So how much the rope, say the rope actually ends there, how much is it extended this way, right? That's equal to the positive version of that number, right? Does that make sense? Yeah. So that's that. The displacement is how much the rope moved, which is that. Okay, now we actually have everything we need to plug it in to our big formula. You ready? So what I've done first is I've written it out as the full formulas like that, right? Sorry, this one matches up to over here. This one matches up to over here, right? Okay, time to start subbing everything in. Force. Force was given in the question as 200 newtons, right? Let's keep it in newtons. Let's keep everything in SI units. Rope displacement, we just calculated. Right? This checks out because when we pull on a rope, it should add work, right? It should add energy to our system. The mass, what was the mass? 7, yeah, thank you. So every time we say mass, replace with 7, right? It starts from rest, right? And we are also told that it goes until it stops moving again due to the spring. So actually it stops at rest. So that whole component is 0, right? Gravity, we're gonna take as 9.81, right? So you might be thinking, shouldn't gravity be negative 9.81? But for the gravitational potential energy formula, because we said that gravitational potential energy increases when we go upwards, right? Yeah, we take it as positive 9.81 in this particular formula, right? Okay. This one is a change in height, right? So think of the final height subtracted by the initial height. So the final height is, let's just call the datum here. The final height is going to be 450 mil above the starting height, right? So that change in height, we actually, yeah, this is 450. This one. I mean, it's minus 0, so yeah. Okay. The spring constant is what we're solving for, right? So we're gonna leave that as is. And this one, right? So delta L2, right? That was equal to this. Right, that's what we calculated in the corner. Yep. And then here, the spring was originally unstretched. Okay. So how I like to calculate it is I kind of just punch in my calculator one bit at a time and make sure I'm not going crazy. So that whole component is equal to 55.623. This component was 0. This component was 30.9015, and this component was half K 0.075. Make sure you remember the squared, right? Because each of these numbers is squared here, right? And we rearrange for K, and we get K is 8,789.87 newtons per meter. You can also express that in kilonewtons if you want, but I'm just going to leave it in SI units. How's everyone feeling? We're doing 6 questions today, and that was question 2. Okay. I apologize if you're still copying this down. In the break, I'll scroll back up to my notes, and I'll scroll back up to my QR code for my notes, in case you want to copy it down and I've gone too quickly. Okay, so here's our next question. It's another what's it called? Work energy question, right? And we need to know this time, we need to solve for what that pulling force P should be, right? In order for, I don't know why I didn't include the question. Yep, we just need to solve for what P should be in order for our diagram to look like this, basically, right? Okay, so we're told in the question that the velocity in state 2, right, which is the second state, is 0.8 meters per second, and it starts at rest. So when it's in state 1, right, which is a state, it starts from rest, right? The unstretched spring length is LO is 200 mil, and we can actually see. Okay, does our spring in state 1 start from the unstretched state? Think about this. Someone might have corrected it. Does because our object is attached to the spring this time, does it start in the spring's equilibrium state, the unstressed state? Yeah. Getting some yeses and some no's. Is it yes or no? No. No. Why is that? Because the wave goes down. So this number is not the same as 200 milligram. So would you say it starts stretched out or compressed? Stretched out. Very good. So it starts stretched out and it gets more stretched out, basically. Right. From state 1 to 2. Okay. So let's first calculate the work portion of our big mama formula, basically, right? So let's think about the rope movement. So we're gonna do a similar thing. This is like a fixed pulley or whatever. And you know, our rope states will look like this and this, right? So essentially that distance is going to be reduced, that diagonal is going to be reduced, and then the equivalent amount of rope is going to be moved in our second state, right? So S1, let's call it, it's going to be equal to, yeah. So I'm focusing on this triangle right here, right? You see the geometry of this triangle? 200 plus 200. Oh, let's do it in meters, sorry. Plus 0.25 squared, right? So that's this triangle, yeah, this hypotenuse of that triangle, right? Okay, S2 is going to be this triangle instead, right? So that's just going to be 0.2, and like that, right? Okay, and now we want to calculate delta S, which is going to be, it's just going to be, oh sorry, let's calculate this out. Delta S is going to be final minus initial, but S is going to be the positive version, right? Because it's to do with the amount of rope which has been moved in the direction of P. Okay, does that make sense? Yeah. Okay. So now we have our big mama formula, and we're going to be solving for P, and we've calculated for S there, right? Like that. Yeah. So now we're just going to plug in the rest of the stuff, right? So here, M, oh, did I ever say it? Oh yeah. M is 0.5 kilograms. 9.81 for gravity. The final velocity is 0.8 meters per second. The initial was 0. Okay. Let's have a look at the height, right? So this is the height, the change in height. Okay. Okay, let me think about how to word this. Okay. So, sorry, give me a second. So this is 200 mil, right? Between, like, how much is moved is 200 mil essentially, right? So that's going to be this line of the triangle. So it's moved, you know, the box is moved from here to here. Let's call it 0.2 meters. And then we know that this whole thing is inclined at 15 degrees. Right? So if we want delta H, right, delta H is going to be 0.2 sine 15. Right? Make sense? because that H component is always directly up and down along your y-axis, right? Spring stiffness, we're told, was 250 newtons per meter. Did I write that down? Yeah, here. And spring stretch. All right, let's calculate this. So, so we know that the spring. Oh, sorry. So we know that the spring started stretched, right? And then it got more stretched, correct? So state 1 is how much it starts over here, right? In terms of its stretchedness, right? So this value should be 0.25 is how far away it is, right? And then 0.2 is its unstretched state. So that one's LO, right? And then here, it goes to 450 mil, right? It's 0.45 minus its unstretched state. That. Again, that's LO, right? Does that make sense? Yeah. So X, remember X represents like a delta L kind of situation. Yeah, this is delta L. So X is all to do with the change in the spring. Oh, sorry, it's deviation from its equilibrium point, essentially, right? Okay. So now we're going to just solve for P. So we're going to divide the right-hand side by this number. And we get P is 52.12 newtons. That's the answer. All right, does anyone have any questions? I'll give you, oh, sorry, question.
Where did you get the 0.45 minus 0.2, 0.25 minus 0.25?
This one, right?
Yeah, this bit.
Okay, sorry, I didn't explain that very well. So it starts here, right? In the first state. This is 0.25 meters, right? What is the spring's equilibrium state? Like length.
0.2.
Length. Yes. That's 0.2. Right? So when we're calculating x1, that's to do with the deviation from that equilibrium state. So we'll just do 0.25 minus 0.2.
Oh, okay, so that's like the first deviation, and the other
Yep.
one is the second deviation.
Yep, and the final deviation is this one, right? Because the spring's equilibrium state doesn't change. What does change is how much you've deviated from it, right? Which is, in the second case, 0.4 meters, right? 4.5 meters. Yep. Okay, any questions other than that? All right, sorry guys. I know it's been a long workshop. I'll give you a break, somewhere between 5 to 10 minutes, and we'll come back and then do the other questions. So that's the energy part. Yep. I'll scroll up to the QR code and stuff if you need it. Yep. Sorry?
We get formation exam. Do we get what's your formation exam?
Oh, I think it's.
Oh yes, that's right.
I think you can bring in whatever. It's just looking in terms. I'm pretty sure.
I'm pretty sure.
Yeah.
I think I know as well. Okay, yeah.
Yeah. There's way too many formulas to remember. Yeah.
I'll grab it.
I mean, they could. I don't remember because I think I did mine during COVID. So that's basically open book anyway. You know what I mean? Yeah. But it could be like formula sheet kind of situation. But if they do give you a formula sheet, then it will be pretty extensive, I think. Yeah. But the formulas I'm giving you is like the mining schools formulas, so they might look a little bit different. I'm not sure if they call it like delta T and stuff for kinetic energy.
It's pretty easy to translate.
Yeah. Like it shouldn't be much. That's
Just like X, right?
Yeah, they might call it something different. I'm not sure. You okay, Brad? I feel like you're dying a little. Like. Okay, fair enough.
What do you reckon?
What do you mean?
Like, there's a lot of stuff. But
Yeah.
it's doable.
easily straightforward.
Yeah. Just lots of steps.
Yeah, it's something where you can do like one thing.
I'll try and question myself. This is something I feel like I can follow up to pretty well, but like I'm not sure until I try it. If I can actually do it.
Yeah, I'm the same. Should be fun.
Knowing me, it's going to be in a week.
Huh?
Knowing me, it's going to be in a week that I actually try it. So, I'm not great.
We'll do it on Sunday.
Where is that on the central and stuff?
Central. I'd do the
Mine's in inertia. Yeah,
Yeah,
I know, that's
I'm
not,
glad.
it's not on there at all.
But isn't that until? Do we do that at all?
We did it for, we didn't do it in our workshop, you know.
He doesn't measure.
It's all together.
Yeah, no, he did. I remember it.
Because I used like a sheet that he had.
Maybe we should start watching him
Nah.
Nah, he's got like the content on the
Yeah. Yeah, but no, they're better anyway. If you could understand it, you could. But I can't keep on.
As if this summer didn't have very hard lectures, but that's this is all amazing.
Yeah. It just is as I'm understanding, so it's really bad.
Maybe they should use Henry and do like very good things, like the Marvel ones.
Well, I'm
Yeah.
tired now, you can't do anything. So strong, he's tired now.
Yeah.
Yeah, apparently he's like asynchronous lectures are that good. Is that what?
They are. They're like, it's so good.
They are much better. I haven't watched them in a while, I'm really slacking off. But yeah, if I was to watch lectures, it would be his.
Well, what's so good about it? Definitely.
They're all blend out.
Definitely.
They're all blend out. He explains everything because you can't ask him a question if it's being recorded live.
Yeah.
So he covers everything. He makes sure he covers everything so you don't have to.
Yeah. Because I always watch it just in normal lectures in math class. I was like, when someone just like, just go know what's going on.
The captain's guy.
Which streaming on also.
A and D.
Who do you have the calculus?
Grossman. The bald one.
You have Jim and Ted.
I have GBK.
Yeah.
Oh. No, I had Grossman and
Yeah.
Chris.
Hey, you guys didn't finish the boys still.
I don't know if we did.
I don't know if we did.
Because Grossman was so slow. Like, he was insane. He was, and then like when everyone told him, he was just like, he just went like too fast. And he never answered any questions on the online stuff.
You can also online people, yeah.
Yeah. There's more
Yeah,
online people
literally.
than there are people
Yeah,
that can speak English for.
No, I remember at some stage in everyone was getting so mad at Kevin on the online because he don't do stuff like
The comments, they're crazy. Like,
Yeah.
Instagram comments, well, probably they're
Yeah. So people get so mad on it. It's a good chat line. But did you do the?
I was Kevin's. Jim. I was in Jim's tutorial.
I get it.
Oh, you should have seen my tutorial. I don't never where he's from, but I thought you were Greece or something. It's like you were correspond. Whatever. You couldn't understand it. He was like pretty smart, like pretty good at math. He just couldn't explain it. He's like dumb at math. And I was just like, and he pretty much made you look stupid if you didn't know the answer. I'm like, otherwise I wouldn't be asking this question.
Okay, cool.
Yeah.
Alright. You guys ready for the second half of this workshop? we're a little bit over halfway, to be fair. Okay, let's see. Okay, so I've basically at this point, in when I was preparing my notes for the mining school, I was a bit more consistent. So I started calling the objects ABC, and then I started calling the states 1, 2, 3, whereas it was a bit mixed around in the energy part. So yeah. Okay. So for impulse momentum, right? Here are our basic formulas. Momentum is essentially the mass multiplied by the velocity, right? So here we have kilogram meters per second. And the impulse is essentially the change in momentum, right, between the states, right? So basically what impulse is to momentum is what work is to energy, right? So it's just the change in that, essentially, right? There's another way to represent it when you manipulate Newton's second law, and that's that momentum is equal to, there's two ways to represent it based on how you manipulate Newton's second law. Impulse is equal to the force multiplied by the change in time, right? It's basically this, but here's the linear version of it. And then for mass, and then there's the mass velocity relationship. So impulse is also equal to the mass multiplied by the change in velocity, right? Sometimes you get force time graphs, which we'll cover at the very end, where we'll have to map out the area underneath the force time graph. And that area is equal to the impulse. Yes, it's equal to the impulse. Okay. Conservation of momentum is basically saying that the initial momentum plus the change is equal to our final momentum, right? And so I can represent it in terms of our, initial momentum, momentum being mass times velocity, plus our impulse, right? You can also say this one. Is equal to our final momentum, right? But in some systems, there is no impulse, there is no change in momentum. So if you have an elastic collision, right, for example, that's like two balls colliding. So in the first state, you have ball A, and then you have ball B, and then they travel towards each other, and then in state B, they're traveling away from each other, right? So they're impacted at some point. And if they elastically collide, there's basically no change in momentum, right? So whatever your input kind of like velocity, I should say like whatever your initial momentums are is equal to the net like final momentum, right? Sometimes you can have a perfectly inelastic collision as well. So generally this is like with vehicles, or sometimes it's with like ice skaters and they hold on to each other after collision for some reason. You know what I'm talking about, right? But like usually it's like two cars crash and then they travel together because they stick together, right? Yeah. And in which case the masses combine, and then there's some combined velocity. Two here referring to the state and time, not the object, remember? Right. Okay. Does that make sense? Yeah. I said yeah really quick. Does that make sense? All right, cool. So here's our next question. So there's a little bit of Newton's second law in here, but there's also a little bit of like conservation of momentum, essentially, right? So essentially the question is asking for what is this tension force in the rope, such that the initial velocity is equal to that. I've converted it from kilometers per hour to meters per second, right? Remember to divide by 3.6, not the other way around. Always remember the school example, right, from last lesson. Okay, and then same with this, right? We've converted it to meters per second. Anyway, so the initial velocity is 8.3, and then the car speeds up to 19.4. So I guess since we're talking about cars, it helps to think about it like this. The initial velocity is 30 kilometers per hour, right? And then they linearly accelerated to 70 kilometers per hour, right? And then this was done over 15 seconds, right? And there's a rolling resistance of 500 newtons. So rolling resistance is literally just another way of saying our kinetic friction. So that's just saying that this frictional force is the constant that's opposing our motion, right? So basically, we don't have to check for the static friction threshold because we're saying that these objects are both moving, and then it's always subtracting off this kinetic friction amount. Anyway, so we have to find T essentially in this. So we draw the free body diagram of the car. I've really simplified it to just a particle, right? But yeah. So the sum of the x forces is equal to mass times acceleration. And let's look at the horizontal forces. So that's the horizontal component of the tension, and subtracting the rolling resistance of 500. So here's one of our equations, right? Okay. Next, we have to think about the momentum equation because this is going to help. I guess when you're looking at these questions, one way to realize that you have to deal with momentum is that, like, usually change in time, this, like when they give you the time period that it's over, usually it's something to do with momentum, right? Or impulse, I guess. Right, so here's our conservation of momentum equation. So the car is 1,200 kilograms, right? And it's going an initial speed of 8.333 meters per second, right? And, okay, I'll come back to this one, right, the force, in a second. This one we know is 15 seconds, right? And the car doesn't change mass or anything like that. It stays as this, right? Oh, I'll just do it over here. And then what did we say it went to? 19.44. Okay, the question is, what force value are we going to plug in for force? Just have a think about this for a second. It's going to be the net force, right? So the net force is equal to this, but it's also equal to this, right? So since we don't really care about the left-hand side, our net force we can express in terms of this force net? I don't know. I just call it the sum of the horizontal forces. It's equal to this entire expression, right? So we literally plug in this, right? Oh, you know what? I can do that the other way around. Right? So, since we know everything except t, we can actually just solve for t straight up in this equation, right? Okay, sorry, I don't know if I explained that last part very well. Do you guys have any questions about that? Okay. Cool. All right, so now we'll talk about collisions, right? So again, we've been talking about, like, let's say two balls colliding, right? And then we can look at the state 1 and 2, right? Where state 1 is before the collision in this case, and state 2 is after the collision, right? And we've called the objects A and B, and this is the notation that we've been using. Basically, we have this new kind of, it's like a ratio, right? We have this new ratio called the coefficient of restitution. So you can think of this like how much of that velocity is maintained after the collision, right? So this number is never going to be greater than 1, right? And it's never going to be a negative number. So if the number is equal to 1, you have a perfectly elastic collision, which means that none of its net speed is lost after the collision. if you have a number that's 0, it means that you have that perfectly inelastic case. So that's where the cars like stick together or whatever, right? That's a perfectly inelastic collision. But then if E is some number between 0 and 1, like this, it's called an inelastic collision or a plastic collision, something like it's called. And this is where a portion of its net speed in that system is lost, right? Due to that collision or whatever, right? One more thing to note, this only affects the normal portion of the collision, right? So basically, because we're kind of analyzing this case in one dimension, right? It's traveling rectilinearly, like on a straight line. We only have a normal portion for that collision, right? So think of it like those are the balls like colliding, right? That's only like normal forces, right, on that collision, right? But sometimes, you know, think of like billiard balls. The collisions might not happen in one dimension. The collisions can happen at an angle, right? So you can kind of have to analyze this in 2 dimensions. And then you can think of it in terms of its normal component and its tangential component. So the normal component is, again, that. The tangential component is its movement, you know, tangential to the other object, right? So when I say the coefficient of restitution only applies for the normal component, we might look at an example. I've got an example, but we'll look at it at the end of the workshop. But yeah. Okay. All right. So here we have a simple question. It essentially tells us that the coefficient of restitution is 0.6, right? Which means that the ratio of the final, you know, velocities is going to be 60% of what the inputs were, I guess, like the initial velocities, right? So, let's just plug in what we know. So basically we know the initial velocities, right? So what we're looking at right now is state 1. This is everything before the collision. And what we care about is what is the speeds of object A and B after our collision have happened, right? So essentially what I'm trying to say is we have 2 unknowns and 2 formulas, right? So these are our 2 big formulas, right? The coefficient of restitution and, you know, conservation of momentum, right? Okay, so our for what we're looking at here for object A, we're taking the positive direction as to the right. Okay, so we say that this is 7 and this is -5, right? So let me just write that out properly. Sorry. 0.6 is equal to VB2 minus VA2 over 7 plus, 7 minus 5. So this is 7 plus 5, right? Okay. So I'm going to rearrange for VB2, and then we get this. And here will be our first equation. You can imagine we're doing simultaneous equations because we have 2 unknowns and 2 equations, right? So we're going to substitute this in a second. So yeah, let's just plug in the rest of these numbers. So the mass of A was 2, velocity of A is 7, mass of B is 3, the velocity, this is the initial velocity, sorry, is -5 for B. The mass is still 2, and VA2 is unknown, and the mass of B is still 3. And instead of VB2, we're going to plug in everything here. Right. So that plugs in there. All right, so when we calculate everything on the left, that gives us -1. 2VA2 plus 21.6 plus 3VA2, right? So we group together the like terms like that. And we get VA2 is negative 452 meters per second. So you can leave it like that, but when we get a negative number, does that mean it's moving left or right? Left. Very good. So great. Now we got to find VB2, and the best way to find VB2 is just plug in our original simultaneous, like our original equation for the simultaneous equation, this one, and we're going to sub in that value we found. And so, yeah, VB2 is 2.68 meters per second, and that's going to the right. Cool. Okay, any questions with that? Great. Okay, so now we're moving on to our last question. This actually wasn't as painful as I thought. But our last question, I mean, there's a few components again. So this is a Newton's second law question. It has friction, and it's to do with impulse, right? So as I've talked about, impulse is about the area underneath a force time graph, right? Which this is a force time graph, but don't be fooled. This is the pulling force only, right? So when we're talking about impulse, right, we care about kind of like that net force multiplied by that change in time, right? If it's linear, right? We have a friction force to account for now. So that net force is not going to be the same as that pulling force, right? So we have to construct another graph to represent this first, and then find the area underneath that graph. Yep. Oh, sorry. Okay. So we should be fairly familiar with the concepts of static and kinetic friction now, right? So the kinetic one should be lower or equal to the static one, right? Okay. So we can start with firstly we can start with the fact that we know mg, right? So again, always start from here. mg is 10 multiplied by 9.81 in this case, right? And then we should do the normal force next. So the normal force you can find from the sum of the forces in the y direction, right? So are we in static equilibrium in the y direction? I think we can safely assume yes, because the pulling forces only are happening horizontally, right? So it's not being yanked up and down and stuff, right?
That should be 98.1. Right?
Yeah, I wrote that wrong. Sorry about that. Thank you. Okay. So basically, let's look at this is our free body diagram essentially, right? We have the normal force and we have mg, right? So as you can imagine, these two things will balance each other out. The normal force is going to be equal to that, right? 98.1 newtons. Okay. So again, okay, well, let's just have a think about what's happening in the question, right? We have a pulling force P. The block is initially at rest, right? It has to overcome static friction, and then it will be moving, where it will be dragged down by the kinetic friction constant, right? So, do we start by assuming that we're in static equilibrium? Yes, we should always check that threshold, right? So to check the threshold, we have to just call this FF for now, as like remember, this is how much water goes in your bucket, right? So it's P minus, let me re-explain this, my bad. So basically, that FF value is going to change over time, right, in this case. So what we're more concerned about is we're going to straight up calculate that threshold value at which the pulling force overcomes the friction, right? So what I mean is, like, what we care about more is what time and what force will we overcome friction, right? So to do that, again, we go back to static equilibrium, but we're just calculating the tip of the static equilibrium peak, right? So again, if the static equilibrium thing looks like this, we're calculating this point here, right? So we call it Fs. So Fs is our threshold number. It's called Fs max. So that's equal to this one times the normal force, right? Our static friction constant was 0.6, and the normal force 98.1, which we calculated previously, right? We're essentially up to the step, right? Okay, easy. So now we just solve for P, right? So what it's saying is at P is equal to 98.86, right? We're at this tipping point for when we start moving. So P is the applied force, right? So at 58.86, that's where we start moving the box, right? So if we think about this as a function, we can realize at what time we start moving the box as well, right? So y equals mx plus b, you can do all that. We know that it starts at 0, so there's no y-intercept. So essentially, P, which is the y-axis, is equal to, what is it? It's 25, right?
Yeah.
Yeah. 25t. That's due to that slope, right? So rise over run. Right, that slope is 25. Yeah. So if we plug in 58.86, we can solve for time. Time is equal to, so this time is when the box starts moving, right? Okay, so great. All our stuff is falling into place. We just need an expression for when the box is moving, right? Which is P minus Fk, Fk being equal to this one, 0.4, 28.1, gives us 39.24 newtons, right? But basically P changes over time, right? And so net force changes over time. So what we've been plotting, anyway, we can plot it like this. So right, when the pulling force is 100, our net force is, did I write that the other way around? Yeah, I think I did, my bad. That makes more sense. Yep, so when our pulling force is 100, our net force is 60. When our pulling force is 58, our net force is 19.6. Yeah, makes sense. Okay, lastly, so we have to calculate the area underneath the FT graph, and note that that's the net FT graph, right? So that's this area here, right? The area of a trapezoid, right? We can integrate it if you want to do calculus and all that crap, but what's easier is we can just find the area of a trapezoid. Brad, can you come up for a demonstration? Yeah. So here's one way that you'll never forget it, right? So let's say you're standing like 2 meters or so away from me. right? If we want to find the area, okay, basically, here's me, here's Brad. We want to find the area of this trapezium, right, between the top of our heads, right, and the distance between us. Let's say that's 2 meters, right? What we have to do for a trapezium, so it's showing. Oh, it dropped out. Okay, ignore that. So to find the area of the trapezium between our heights and 2 meters, right? First we have to average our heights. So Brad's probably a little bit taller than me, right? So we go like that, we average the heights, and then we multiply it by 2 meters. Every single time for a trapezium, like through civil engineering, sorry, you can take a seat. Thank you. Through civil engineering, you need to use this formula a lot. That's, in my opinion, that's the best way to remember it. It's like super random, but you won't forget it because of how random it is. Yep. Okay, well, I've dropped out on Discord, but I'll just show you it. Basically, J is half the height of this, so 60.76 plus 19.62, and then we multiply it by that distance between those two, and then that whole thing.
The world is ending today.
He was lying.
Okay. So
Damn.
that's J, right? And then this one is M delta V. M is 10. This one is V2, and it starts to rest, right? So we can calculate V2 if we rearrange all this, and then this is the speed of the box after it's been pulled for 4 seconds, increasing the speed from increasing the pulling force from 0 newtons to 100 newtons over 4 seconds. Yeah. Okay. That's the end of my workshop. If you have any questions, come up the front, but otherwise, you're free to go.
They didn't give much time for us to let it out today.
No, it's like 2 weeks.
I mean, it is the civil experience, I guess.
Yeah.
Well,